Here's a system of 3 equations and 3 unknowns, and in this section we're going to investigate a method for solving this system. We could use methods that are very similar to the ones that we've already talked about. That is, we could use a method of graphing. Now, to use graphing, though, if you think about it, we have at our disposal on a graphing platform on a Cartesian plane, we have an x-axis and a y-axis. Well, if we have 3 unknowns, we'd have to have a third axis. We would have to have a z-axis. And we could actually imagine that. We could have our x-axis, a y-axis, and a z-axis that comes out from the board or goes through the board kind of like this. So it would be a 3-dimensional coordinate platform. And we could actually form coordinates of points in ordered triplets, you see. An x value, a y value, and a z value giving us distance this way, you see, in our coordinate plane. And if we plotted points like that, these equations would form flat surfaces. That is, we would have planes for the graph of each of these. And it's the intersection of those planes that we would be looking for in order to find a solution for the system. Well, although that's theoretically possible, we don't have at our disposal a very handy 3-dimensional graphing platform, and so we just won't use that method. The other methods, the method of elimination and the method of substitution, work as well. That is, we could substitute. And I mean, think about this. We have 3 equations and 3 unknowns. We take one equation. We solve the equation for one of the letters. Any letter, any equation. We put that information back into the other 2 equations. Now we have a system of 2 equations and 2 unknowns. And then we take within that system, we massage it, simplify everything, and then in one of those equations we solve for one letter, and then take that information and put it into the other equation. And now we've reduced it down to 1 equation and 1 unknown, and then when we solve that for that letter, we back substitute all the way through and arrive at a certain solution. Well, although possible, it is highly manipulative. That is, it's algebra intensive. And we have to keep track of a lot of things. There are more expedient ways of solving systems of equations that involve more than 2 variables. And generally speaking, if we have 3 variables involved, then we need 3 equations. If we have 4 variables, we need 4 equations. If we have 5 variables, we have 5 equations. You get the picture. And can you imagine what we would have if we would have 10 variables and 10 equations, and how we might have to deal with that situation? Certainly the idea of substitution would not be a workable kind of thing. We would like to get to the point in our discussions here eventually where the feasibility of handling a system which is pretty big, like 5 equations and 5 unknowns, is not completely unreasonable. Well, the method I'm going to show you is a method that you haven't seen in the past, and so this may seem a little confusing at first, and because of that you might need to rewind the tape and play it again, maybe a couple of times, to get the hang of this. But here's what we're going to do. We're going to manipulate the system of equations in ways that are consistent with everything we've talked about. That is, we're going to be able to exchange one equation for another in terms of position. We're going to multiply through equations by a particular amount, and we're going to be able to add or subtract the equations with one another. Those are all operations that we performed in the past. We're just going to perform those operations in a particular way in order to try to arrive at a particular structure for the group of equations. That is, we're going to take this group of 3 equations and 3 unknowns, and through a series of steps where we write equivalent systems, we're going to get to a system of equations that looks like this. Now, you might be thinking, well, how is this helpful? Well, it's helpful because the back substitution process here is extremely easy. If we have our third equation telling us that z is 3, then certainly we can replace z with 3 in this equation and solve for y. And then if we have y and z in these 2 equations, you see, then we can substitute into our first equation and find the value of x. So that's the whole idea. Now, this form of our group of 3 equations and 3 unknowns is called row echelon form. row echelon form. Now let me tell you the characteristics of this form. In the first equation, the leading coefficient is 1. That's one thing. The next thing is that there are no x terms in our other two equations. The next idea is the leading coefficient in the second equation is 1. And there is no y term in our third equation. The last characteristic is that we have a leading coefficient here of 1. Now, with those characteristics, we have the layout for row echelon form. The method used to move from this kind of group of equations to this row echelon form is called Gaussian elimination. And with this Gaussian elimination process, we go through this thing. Now, let's go through and understand that we're going to try to accomplish certain items in this road to row echelon form in a certain order. And the first order of business is to accomplish a leading coefficient of 1 in our top equation. Now, we already have that here, so we don't have to manipulate for that goal. Now, sometimes to manipulate for that goal, we have to exchange equations. For example, this equation could occur down here as equation number 3. Just imagine these two being exchanged. Then the first thing that we would do is just exchange them in order to accomplish this. All right, that's the first order of business. The next order of business is to eliminate the terms involving x in the other two equations. And we do that like this. Now, organization is the big key here in accomplishing this whole task. And toward that end, we're going to make some notes here about what we're doing in terms of manipulation. And to keep things straight with our three equations, we're going to draw this kind of thing. We're going to bracket the three equations. Because when we write another step down here, we're going to have another group of three equations, and we don't want to get these confused. Okay, so in our next bracket, you see, I'm going to begin by rewriting the top equation. I want to maintain the equivalence of this group of equations with this group of equations. So I'm going to bring down the first equation. Now, my goal is to cause a vacancy to occur right here. And in order to do that, I'm going to simply add these two equations and put their sum right here. You see, I'm going to add those two because x minus x is going to be 0x, and I'll have the vacancy that I want in this position. Now, in order to keep track of what I'm doing, in order to make notes of the operations being performed, I'm going to make those notes out here to the left of this bracket. I'm going to say over here what I'm going to do, and I'm deciding what to do right here by looking at these terms. So all I'm doing is adding the two equations. I'm taking equation 1 and I'm adding equation 2. All right, let's do that. Add these two, we get no x, as expected. Add those two. Negative 2y plus 3y, oh, that's 1y. Add these two. 2z with no z, that's 2z. And then 9 minus 4, 5. Okay, the next order of business is to create a 0x or no x term right here. And to do that, we play these two off of one another. Now notice that I'm using our top equation, and I am also using this third equation, and I'm going to perform operations involving those two equations in order to accomplish this vacancy. Now I have to do two things here. I have to multiply in equation 1 by negative 2. I have to go negative 2 times x is negative 2x, and then add this. So I'm doing two things at one time, but it's not too difficult to do that as long as all I'm doing is multiplying here and adding with that. And that's what I'm going to indicate here. So I'm indicating negative 2 times equation 1 plus equation 3. So negative 2 times x is negative 2x plus 2x, 0x as expected. Then negative 2 times negative 2y is 4y. 4y minus 5y is minus y. Then negative 2, now if you get confused as to what we're doing, refer back to our note here. You see, it's negative 2 times every item in equation 1 plus the item in equation 3. All right, negative 2 times 2z is negative 4z, plus 1z is negative 3z. Negative 2 times 9 is negative 18, plus 10 is negative 8. All right, now I want to go another step. Now I've accomplished the 1 as the leading coefficient of the top equation. I've accomplished vacancies below that. The next order of business is to come down here sort of on a diagonal pattern and accomplish a 1 as the leading coefficient for this second equation. Oh, it's already done. We don't have to do that. All right, the next order of business is to accomplish a 0 or a vacancy for this entry. All right, let's do that. We can do that by adding these two. But let's not get ahead of ourselves. We need to write these two equations down. This one is in the form that we want, and this one is also in the form that we want. So we're going to be working on equation number 3. So we'll take equation 1 and just bring it down. And equation 2, just bring it down. And now, we want to cause a vacancy in this position. We do that by just adding those two equations. Now notice that we are playing these two off of one another now. We're not working with equation 3 and equation 1. If we were to manipulate with those two, it would create a situation down here with the x, which we don't want. So once we have created that 1 coefficient, the leading coefficient of 1, that's when we can play off of that equation and cause the vacancies to occur that we're after. Now I know about right now you're thinking, gee, this is so difficult. This is just incredibly complicated. Maybe you're thinking that way. But once you get the hang of this, just a couple of problems, it will go rather quickly. In fact, you'll make your decisions very, very quickly in this kind of environment. And if you write down the decisions that you're making, that is, make your notes properly, you're not going to have a great deal of problem with this. All right, we're going to add these two. Now, we're going to take equation 2 and add equation 3. You see, just add those two. Adding these two, we get this. And the result we're putting along this line, you see, along this, for this third equation. All right, add those two, we get a vacancy here, as expected. 2z minus 3z is minus z, and then 5 minus 8 is minus 3. Okay, now, we're almost there. All we need to do now is manipulate our group of equations so that this leading coefficient is 1, and we can accomplish that by either multiplying or dividing by negative 1 in equation 3. So I'll come up here to the top and I'll just rewrite equations 1 and 2. So here's what I do. Now, I'm going to write what I'm doing over here, perform the operation, and then put the result right here. I'm taking that equation 3 that was down here to the left, and I'm multiplying it by negative 1. So it's equation 3 times negative 1, or negative 1 times equation 3, however you'd like to write it. But it turns out to give us z equals 3. Now, this is the form, this is the row echelon form that we mentioned that we were targeting. And once we arrive here, we go through the matter of back substitution. That is, since we know from equation 3 that z is 3, then we take equation 2 and replace z with the value we found for it. And this is a z. Sometimes you'll see mathematicians and others put a little mark through the z like this to make sure that you know it's an alpha character rather than a 2. But at any rate, we have this. So this is, let's see, this is 6. Subtract 6 on both sides. We find y to be negative 1. So let's see, we have z is 3, y is negative 1. Now, with that information, on z and y, we can find x by going back into equation 1. So equation 1 is x minus 2y plus 2z equals 9, and then x minus 2 times negative 1 plus 2 times 3 equals 9. And now let's see, this is x, this is 2 plus 6, that's 8. Subtract 8 on both sides, we find x to be 1. Now we found x to be 1, y negative 1, z 3, and our answer can be written as an ordered triplet. The triplet is, let's see, x, the first component of the triplet, is 1, y negative 1, and z 3. So the answer is written like this. I'm going to just put a box around it to emphasize the idea. Now this is the solution to the system of equations, which means if we replace x with 1, y with negative 1, and z with 3 in each of those three equations, the statement will be true. All right, so that's the idea. Here's another system. We're going through the process again, and I want to show you a couple of the nuances that can occur here. There are some manipulative tricks that are used in this environment, and we'll see a couple of those here. All right, let's see. We'd like to cause the leading coefficient up here to be a 1. Now, we can cause that to happen by swapping equations, or by adding a couple of equations or subtracting them, or dividing through an equation by a particular amount. Now, because we have so many options like that, there are several ways that are possible and correct to work these problems. So just one way, just because you work it one way and it's right, doesn't mean that's the only way. And because you see me work it one way, doesn't mean this is the only way to work it correctly. You might have another way that works just as well, maybe even better. But I'm going to select a way of working this, and I'll describe for you two ways. One is to take 3x and subtract 2x. You see, that'll give 1x. Put the result up here as equation 1. You see, play these two off of one another. Now, in order to accomplish that, you'd have to put equation 1 somewhere else, you see, and then you'd have to play these off of one another and go through that process. Well, that's possible. But another possibility is to look for a situation where you can divide through by some constant. And in equation 2, we can divide through by 3, you see, and accomplish that leading coefficient of 1. So we're going to do two things in this step. We're going to take equation 2, and we're going to put it up here, and at the same time we're going to divide through by 3. So we're taking equation 2 and dividing by 3 and putting the result here. Let's go. Equation 2, divide by 3, this becomes x. This becomes y. Vacancy here, and then 9 divided by 3 is 3. All right, now we have replaced the original equation 1 with equation 2, so we're going to have to just put that rascal in equation 2's place. So we're going to just put equation 1 right here. So that's 6y plus 4z equals negative 12. And then I'll bring down equation 3. All right, and away we go. We've accomplished the first task of having a 1 as the leading coefficient in equation 1. The next task is to cause these two items to be a vacancy. That is, eliminate the x here, eliminate the x here. The x is eliminated here, so there's nothing to do. So in the next step, then, I'm just going to bring down equation 1. And equation 2. And in order to clear this 2x, in order to have a vacancy down here in equation 3, I'm going to need to play these two off of one another. So I'm going to multiply in equation 1 by some amount and then add equation 3. And I'm indicating what I'm doing down here. All right, so that's the idea. So it's going to be negative 2 times equation 1 plus equation 3. That's what I'm doing. Negative 2 times x is negative 2x plus 2x, 0x as expected. I think I need to give myself just a wee bit more room down here. Okay, Now, let's go through the other terms and do the same thing. Negative 2 times y, negative 2y plus vacancy is negative 2y. Negative 2 times vacancy is nothing plus negative 3z is negative 3z. Negative 2 times 3 is negative 6 with 10 is 4. Now, we've just noticed another nuance. That is, we've noticed what we do when we have vacancies already in our system of equations. You just treat the situation as though you have 0z here, 0x here, 0y here, you see, and then you're okay. So it follows intuitively with what we would probably expect. All right, the next order of business is to cause the leading coefficient in equation 2 to be 1. Now, a lot of times, to accomplish that, you play these two off of one another. But in this circumstance, it's difficult because if we were to even multiply in, well, one or both of these equations and then try to add the two equations, we're not going to arrive at a difference of 1 because, after all, they're both even. Now, a way to deal with it is like this. We could divide here by 2, and have 3y plus 2z equals negative 6. And then we have that difference that we're talking about. Then we could add the two equations. Another way is to just very quickly divide through here by 6. Now, if we divide through by 6, notice the 4 divided by 6 doesn't go sort of evenly. We would have 4 6, we would have a fraction involved. And when you begin to involve fractions in these problems, sometimes the problem can get algebraically out of hand. So you need to be careful about that. I'm going to show you the problem that way, this particular problem that way. But just realize that if you do that early in a problem, that sometimes it can get away from you. But I've done this problem before in practice for this demonstration, and so I know it's not going to be too awful. So anyway, here we go. Now, I'm going to come up here, and we're going to have to be looking back and forth here between these two, but I'm going to write this down, just bring it down up there, and then divide here by 6. I'm dividing 6 by 6, 4 by 6, and negative 12 by 6. But I'm going to do it all up here. Here we go. So I'm bringing down the top equation, that's x plus y, and then no z, and then a 3. And in the second equation, I am taking equation 2 and dividing by 6. And when I divide the y term by 6, I get y. And when I take 4z and divide by 6, I get 4/6 z, which is 2/3 z. And then when I divide the negative 12 by 6, I get negative 2. All right, and the third equation I'm not operating on at all because my task at the moment was to accomplish a leading coefficient here of 1. So I'm just bringing down equation 3. Now the task in the next step is to eliminate the y in equation 3, the y term in equation 3. So we'll begin by bringing down the first two equations. We have x plus y equals 3, and here we go. All right. In order to do that, we need to operate on equation 2 and then add the two equations. So we'll multiply in equation 2 by 2 and then add equation 3. And we'll indicate what we're doing here. So it's 2 times equation 2, then plus equation 3. All right, 2 times y, 2y, minus 2y, 0y, as expected. Then 2 times the 2/3 plus the negative 3, you see, as the coefficient on z. Now here's where the situation gets a little bit unruly. It gets a little bit arithmetic intensive when we begin to involve fractions. And this is what I was warning us about just a little bit ago. So here's what we're thinking. We're thinking, okay, 2 times 2/3, well, that's 4/3. And then subtract 3. So this is what we're doing algebraically. I think the fastest way to do it is to think of 3 as 3 over 1, multiply by 3 over 3 in order to accomplish a common denominator. So we'll have 4/3 minus 9/3. Oh, that's 4 minus 9, negative 5/3. So it's negative 5/3 then, z equals, now, I forgot what we're doing. Well, let's see. We are operating according to our notes here on equations 2 and 3. So it's 2 times equation 2, that's 2 times negative 2, whoops, up here, 2 times negative 2, and then plus 4. 2 times negative 2, that's negative 4, plus 4 is 0. That's what makes the situation pretty nice, because think about what needs to happen in the next step for us to cause a leading coefficient here to be 1, because that is our next task. While you're thinking about that, I'll erase this. All right, in order to cause this coefficient to be 1, we divide on both sides by this coefficient. You see, we divide on both sides of the equation by negative 5/3, and when we divide over here by negative 5/3, we get a 1 as our coefficient, and when we divide over here by negative 5/3, we get 0. So it comes out okay. Now let me bring down these. And now I'm operating on the third equation only, and I'm taking equation 3 and dividing by the coefficient which is there, which is negative 5/3. And when I do that, I get 1z equals 0. Now it's particularly easy to back substitute to find the values for y and x. Let's see. If z is 0, substituting that information into equation 2, replace this z with 0, this term goes out altogether. So y is negative 2. You know, I can begin to build my ordered triplet right now. I'm thinking, gee, I have an ordered triplet. I have a first component, second component, third component. Z is 0, so I can put that here. Y is negative 2. That goes here. And now let's find x. Well, if y is negative 2, then in equation 1, we replace y with negative 2. So we have, let's see, x minus 2 equals 3. Add 2 on both sides, and we find x to be 5. So the ordered triplet 5, negative 2, 0 solves the system of equations. Here's a third one. We're going to go through the process one more time. And just remember or try to anticipate what we're going to do at each stage of our development toward the row echelon form. The first order of business is to cause the leading coefficient of our first equation to be 1. It's not 1 here, so we need to do something. And the something that we do is either take this equation and put it up there, or this equation and put it up there. And it doesn't make any difference which one we choose to put up there. All right, so here's what we have. I'm going to create a little room here for instructions. And here's what we're doing. We're just going to take, let's just take equation 2 and put it here, and equation 1 and put it here. So we're just exchanging those two. We'll have x plus z equals 2, and then 2x plus 3y minus z equals 1, and then x minus 3y plus 4z equals 5. Now what we've done, if we want to write an instruction for this, even though it's rather trivial, we might just put something like this, that we just exchange the two equations. You see that, or we could put that this was equation 2 and this was equation 1, and we exchange them. You know, something like that to indicate what you've done. All right, now let's jump into the next part of what we need to do. We have the leading coefficient of 1, job done. Next job, cause these two entries to become zeros, that is vacancies here. So we're going to not operate on equation 1. It's okay as it is, so we bring it down. We're going to operate on the other two. Now to cause this entry, this second entry down here to be a 0, we're going to need to multiply in equation 1 and then add equation 2. And we've done this same kind of operation a couple of times before. We're going to multiply in equation 1 by negative 2, and then we're going to add equation 2. So it'll be negative 2 times equation 1 plus equation 2. Now notice the format of the instruction here has almost always been that we show what we're multiplying times some foreign equation, and then we're adding the equation we're in. That's basically the format for our instruction each time we have this operation and addition to perform. All right, so performing this operation, negative 2 times x, negative 2x plus 2x, 0x as expected. Negative 2 times vacancy for y is no y, plus equation 2 plus the 3y is 3y. And then negative 2 times 1z, negative 2 times 1, negative 2z, then minus 1z is minus 3z. And then negative 2 times 2 is negative 4, plus 1 is negative 3. All right, now we look around, what's the next thing we need to do? We need to cause this to remain a vacancy here. So we need to clear this x. And we play these two off of one another. So it'll be negative 1 times equation 1, or simply the negative of equation 1, plus equation 3 to accomplish that. Negative x plus x, vacancy as expected. Negative, nothing with equation 3, that's negative 3y. Then negative 1z plus 4z is 3z. And then negative 2 with 5 is 3. All right. Our next task would be to cause our leading coefficient in equation 2 to become a 1. And we're going to go up here to do that. Now, all we're doing to cause that to happen is we're dividing through by 3. So this will become y minus z equals negative 1. And that's all there is to it. So I'm going to do that up here, and then I'll just bring down equation 3. So this next item is fairly easy. Okay, first equation is fine. Dividing through on this one, we have y minus z equals negative 1, as we said, and we bring down the last equation. Think about the next thing we need to do. All right, we have a 1 here, we have vacancies here, we have a 1 here, we need a vacancy here. So the next thing we're going to do is, I forgot to write my instruction here. It was equation 2 divided by 3 in order to accomplish this. Okay, now we need a vacancy here, so we're going to play those two off of one another, and that means we're going to multiply here and then add that. So we're going to bring down our first two equations because they don't need any help. All right, here's what we're doing. 3 times y minus 3y. That is 3 times equation 2 plus equation 3 is what we're doing. So 3 times y, 3y, minus 3y, no y as expected. 3 times minus 1z is minus 3z, plus 3z is 0z. The z's went out. We have 0 here. 3 times negative 1 is negative 3. Negative 3 plus 3 is 0. Wow. All of the letters went out of our system of equations. Well, we know from past experience that when that happens, something funny occurs. That is, we have one of two situations before us. We either have no solutions or we have an infinite number of solutions. Now, we have no solutions when the resulting statement of equality is false. But we have a statement of equality that's true. 0 is equal to 0. So that means that we have an infinite number of solutions here. Now, your teacher may allow you to stop right here and just say an infinite number of solutions, many solutions to this system of equations. Or your teacher may want you to generate some way of writing the infinitude of solutions for this system. And that's what we're going to do. I want to show you a technique for writing all of the solutions, or for generating solutions within this system. What do they look like? What values are there? There are an infinite number of ordered triplets that solve this. We know that right now. But what are they? Name one. You see, that's kind of what we're after. All right, it turns out that all we're going to do is write relationships among x, y, and z from these two equations. And here's what we'll do. From equation 2, I can solve this for y by adding z on both sides, and I have y equals z minus 1. Now, at this point, you want to let another letter stand for either y or z. And there are many right ways to do this. At this point in the problem, there are many correct ways to illustrate that ordered triplet that will generate solutions to the system. Here's one way. I'm going to let A stand in for Z. Now, A is any real number. So if Z is any real number, then Y is A minus 1. And you see, my ordered triplet is kind of shaping up like this. I have 3 positions here, and the Z, the third item in the ordered triplet, is this any real number. And the second item in the ordered triplet is this any real number that I chose for the last one, minus 1. So this is A minus 1. Now, what does the first item in the ordered triplet look like? Well, we can find out by taking this equation and solving it for x. All right, so solving this for x means I would subtract z on both sides. So I have x equals minus z plus 2. But z was a. You see, a was standing in for z. So x then, in terms of this a, is minus a plus 2. So minus a. Let me create a little room here. Now, here's how you generate the ordered triplet for solutions. Just choose any real number for A. Let's say, 4. So if A is 4, then A minus 1 would be 4 minus 1, and minus A minus 4 plus 2 would be minus 2. So one ordered triplet that solves the system is negative 2, 3, 4. Another one would be, well, let's choose a value for A like 0. So if this item is 0, then we have 0 minus 1. We have minus 0 plus 2. So this ordered triplet also solves the system. Now you would generate exactly the same set of ordered triplets if I had let the y here be A and then solve for z. Now let me show you what that looks like. I just want to make sure we understand this little process here at the end. And we're using a letter like A because we want our triplet, we want every item in the triplet to be based upon any real number expressed in it, not just an x, y, and z, which happens to appear in our system of equations. We don't want a first element, second element, third element to appear in this general ordered triplet. All right, so here's what we can do. Now, the second equation was this. I'll just repeat it right here. And I said we could let A stand in for either one of these letters. Well, we let A stand in for the Z. Let's let A stand in for the Y and see what happens. Now, what this means at this point, as soon as we say, okay, we're going to let A stand in for the Y is the second element in the ordered triplet. Okay, so the ordered triplet is shaping up like this. Here's the A, you see, as the second element. Now, what's Z? Well, let's solve this for Z. We have minus Z equals minus A minus 1. Multiply through by negative 1, we have Z is A plus 1. So the third element is A plus 1. Now, what's the first element? Well, we refer back to that other equation, that x plus z equals 2. and z was a plus 1. So x then is minus a plus 1, you see? And so we have minus a plus 1 here for the first item in the ordered triplet. So here's a way of representing the ordered triplet, and that was another way. Let's see if we generate the same values that we did before. One of the values here in the ordered triplet was negative 2, 3, 4. Let's see if we get that over here. If we let a be 3, then this is a plus 1, 4. You see, and negative a plus 1 would be negative 3 plus 1, that's negative 2. And that is the ordered triplet that we had over here before. So we generate the same group of ordered triplets using this representation, this general representation for the ordered triplet, as we do for this general representation.